Salut tout le monde, it is me, Anthony, obviously, back again with another differential geometry reading stream. It is currently about 6:05 in the morning right now on a Sunday. So I'm wearing my blue light glasses. Arguably these aren't the best because they're not wraparound and the lenses are not actually visibly tinted red, but they definitely do block out blue light. They definitely work. I feel the effects, but I've found that the best time for me to wear blue light glasses is early in the morning right now before actual sunrise, and then actually at the end of the day just before like 6:30, so between like 6 and 6:30. If I wear blue light glasses during the day, I find out that that just makes me too tired to actually function like during the day. Like it makes me feel like I'm about to go to sleep. So I don't wear blue light glasses completely throughout the day. Anyways, I'm making shirts. Last time I talked about making these figure 69 shirts, cone. It also says Anthony makes videos, obviously, and it's got the I don't know what to call it, the exasperated nose exhale emoji, and then the handshake, and then the infinity, and then the geometry triangle emojis. So I'm still trying out different vendors. This is custom ink. I might make a video where it's like Amazon versus custom ink versus whatever, and like compare all the shirts and make its own video of that, because that might get a bunch of views. But I tried out Amazon as well, but when I uploaded the image to Amazon, there was a black background instead of doing a transparent upload is what I did, and so it actually printed on that one the black onto a black shirt. So I ordered it again, and that one's supposed to get here tomorrow, but this one's the custom ink one. The problem with this one is I accidentally ordered like a soft style shirt before I had ordered another one which was not the soft style, which felt like it was like a more substantial piece of fabric, and I think I might like that other one more. But the real downside to custom ink is that it's a little bit expensive, so I really have to like buy a huge volume in order for it to like work out. So I don't know, that's why I said just trying it, but look out for some shirts soon, I guess. I don't know, I'm not in a rush for that. But today for the reading, I'm going to try to get through 2 sections, but I'm going to kind of take my time, and in the beginning here I'm going to try to do a little bit of a review, because I've mentioned this before, which is differential geometry. A lot of the layers of abstraction build up on each other in order to get to new concepts, ideas, theorems, and whatnot. So if you start to forget some of those other abstract layers, then once you get to the new stuff, you could be like, hold on, what's going on here? And so we are in chapter 6, which is on mappings, and this is section 59, spherical image of a surface, third fundamental form, isometric mapping of developable surfaces. And then, okay, section 59, we just got the first mention of the third fundamental form. And you might be dropping into this video and you're like, this is the first differential geometry reading stream I've watched. There's 3 fundamental forms. What is a fundamental form? Why is it fundamental? What happened to the first and the second one? Oh, so yeah, you could be skimming this section and there are these, I mean, maybe it's not obvious if you just drop in right now, but there are these terms which I think are key terms in this book at least, and maybe in this kind of level of manifold theory. We have mention of the formulae of Weingarten, and we have Gaussian and mean curvature. Curvature, that gets tossed around all the time. I guess you could say that curvature gets tossed around in this book as much as physicists like to toss around torsion. Curvature and torsion are kind of very related in differential geometry. So what is all this stuff? Well, in this book you could go to the back where there's a collection of formulae. You open the back of the book and you look this up, you say, okay, what is the first fundamental form? Okay, right? We're in section 59, we're looking at the third fundamental form. What's the first fundamental form? And it says here in the back of the book, okay, we have ds squared equals g sub alpha beta times du alpha times du beta, where g sub alpha beta is equal to the scalar product between vectors x sub alpha and x sub beta. And in this case, well, g sub alpha beta is equal to g sub beta alpha. Okay, we have this commutativity of indices, great. And then the discriminant of the first fundamental form, lowercase g, is equivalent to the determinant of g sub alpha beta, which then calculates out to g sub 1, 1 times g sub 2, 2 minus the square of g sub 1, 2. We have a little more stuff, but it's all already, it's like, well, what does that even mean? Okay, formulas are really helpful if you want to implement something in a computer program, or you want to actually calculate something that's then useful, you know, a quantity that you want to make a decision based upon or something like that. But it's like, this doesn't give me a lot of intuitive insight, to be honest. And you could go further on, and it's kind of the same thing for the second fundamental form. It's the b sub alpha beta times du alpha du beta. So looking at the formulas, I mean, you can kind of see that there is some structural similarity, right? Because we have these scalar products of vectors going on. So the first fundamental form, g sub alpha beta, is the scalar product of x sub alpha and x sub beta, where those are both vectors. For the second fundamental form, well, it's not a g, it's a b this time, and it's b sub alpha beta, but we have a vector which is x sub alpha beta, scalar product with now n, which I'm pretty sure is a normal vector. Not I'm pretty sure, I know it is. But I mean, if you're seeing this for the first time, what might a vector n otherwise stand for? You know, people will just assume that it's a normal vector perhaps, right? But we also have a discriminant for the second fundamental form, likewise as having one for the first fundamental form. But still, it's like, what does this all intuitively or geometrically mean? So I pulled up our good old cat GHB, and I basically asked it this question where I was like, summarize what is the first and second fundamental form, and I asked it about a few other curvatures. So what is principal curvature, Gaussian curvature, what is mean curvature? Spits out 10-paragraph answer, and then at the very bottom we have what's useful for right here, right now. Summary of key points. The first fundamental form measures distances on the surface. The second fundamental form measures how the surface bends, which gives a notion of curvature. And then we have principal curvatures, the maximum and minimum bending of the surface at any point. Gaussian curvature, the product of the principal curvatures, classifying surfaces into domes, saddles, or flat shapes. Mean curvature, the average curvature used to describe the overall smoothness of a surface. So definitely those, the ones about the fundamental forms, it's a little more helpful. And so you're starting to say, oh, okay, maybe I'm starting to get it. We have a surface. Somehow you have to define vectors on this surface. And so measuring lengths, having metrics of length on these surfaces is helpful. Being able to map infinitesimal lengths on the surface to infinitesimal lengths in the coordinate system that the surface is embedded within, something like that. And okay, well, principal curvatures, the maximum and minimum bending of the surface at any point. So out of all of the different kinds of coordinate systems that you're imposing on these surfaces, which ones are the ones where when you define using those coordinate systems, you get these vectors so that you can maximize or minimize some of these dot products that are going on, okay? The other thing that I mentioned a little bit ago was the formulae of Weingarten. So I had a segment like this in an earlier reading stream that I call Meow. Math in your own words, M-I-Y-O-W. And so this is a point in the review where I would like to try to explain in my own words what the formulae of Weingarten are. This is me reading something I wrote down earlier, analogous to representing t dot, p dot, and b dot, so the first derivatives of the tangent, the principal normal, and the binormal vectors at a particular point on a curve. And these, when I say t dot, that means the first derivative with respect to arc length of the vector parametric representation of t, the tangent vector. So analogous to representing t dot, p dot, and b dot in terms of t, p, and b in the formulae of Frenet, the formulae of Weingarten and Gauss are the equivalent in the theory of surfaces. So that's exactly what I just said, basically. So yeah, I don't know, that's something that's kind of nice about the whole differential geometry thing, is even though there are the layers of abstraction and the formulas can seem obtuse, if you just get your hands dirty with this stuff for like 20 minutes and kind of toss it around, now we're ready to go, I feel like. We're definitely still in a part of the PDF where there's a lot of pages missing, and it seems to me that that is because these are starting to be some really important topics, because the entire section on conformal mapping is gone. And so, I don't know, 6:35, top of the morning, let's get this. I don't know, I'm just trying to give you guys an honest take on what it's like swimming through the math in real time, you know what I'm saying? Section 59, spherical image of a surface. Third fundamental form, isometric mapping of developable surfaces. In the theory of curves, the spherical image enabled us to draw some conclusions on the geometric properties of a curve. Analogous possibilities exist also in the theory of surfaces. We impose a parallel displacement to the unit normal vector n in terms of u1 and u2 to a surface capital S whose vector parametric representation x is in terms of u1 and u2, and bind it at the origin capital O of the Cartesian coordinate system in space. Then the terminal point of the vector n lies on the unit sphere S star with center capital O, and to every point of capital S there corresponds a certain point of S star. The position vector of the image of a point of capital S is the corresponding unit normal vector n bound at capital O. The mapping thus defined is called the Gaussian spherical mapping of S. The set of all image points is called the spherical image of capital S, the surface. Let capital S be of class R greater than or equal to 2. Obviously, the first fundamental form of the spherical image of S is given by the expression ds star squared is equal to c sub alpha beta times du alpha times du beta, where c sub alpha beta is equal to the scalar product of n sub alpha and n sub beta. And this is sometimes called the third fundamental form of the surface S. Hence, we now have three fundamental forms altogether. The first fundamental form, which is equal to ds squared, which is given by the scalar product of dx with dx, which are both infinitesimal vectors. Similarly, we have the second fundamental form, which is equal to the scalar product of negative dx with dn. And finally, we have the third fundamental form now, which is given by ds star squared, which is given by the scalar product of dn with dn, which likewise are both infinitesimal vectors. By means of the formulae of Weingarten, we may represent the coefficients C sub alpha beta, which is equal to the scalar product of n sub alpha and n sub beta of the third fundamental form in terms of the coefficients of the other ones. Namely, C sub alpha beta is equal to B sub alpha superscript gamma times the vector x sub gamma, then scalar product with B sub beta superscript nu times the vector x sub nu, which then is equal to B sub alpha superscript gamma times B sub beta superscript nu, then times G sub gamma nu, which is equal to then just B sub alpha superscript gamma times B sub beta gamma. Hence, C sub alpha beta is equal to B sub alpha kappa times B sub beta gamma times G superscript kappa gamma. In consequence of this representation, C sub alpha beta is a covariant tensor of second order which is symmetric. Namely, C sub alpha beta is equal to C sub beta alpha as follows from 59.59. That's what I just said. That's why I didn't write it down. Okay. For the discriminant C of the third fundamental form, we find that C is equal to a determinant where column-wise it is C11, then C21, and then the next column is C12, and then C22, and this 2 by 2 determinant expanded out is then column-wise another determinant which is B sub 1 kappa times B sub 1 gamma times G superscript kappa gamma. The next entry in the same column is then B sub 2 kappa times B sub 1 gamma times G superscript kappa gamma, and then in the next column we have B sub 1 kappa times B sub 2 gamma times G superscript kappa gamma, and then in the next entry of the same column B sub 2 kappa times B sub 2 gamma times G superscript kappa gamma. And this 2 by 2 determinant expanded out is then equal to B squared times the 2 by 2 determinant of column-wise G superscript 1, 1, then G superscript 2, 1. And then in the second column we have G superscript 1, 2, and then G superscript 2, 2. Hence, in consequence of the previously given transformation where we have G star, where G is a discriminant of the first fundamental form, this is equivalent to G superscript 1, 1 times G superscript 2, 2 minus the square of G superscript 1, 2. This is all equal to 1 over G. So in consequence of this, we thus have that C is equal to B squared over G. Furthermore, capital K times the first fundamental form minus 2 times capital H times the second fundamental form plus the third fundamental form equals 0, where capital K and capital H are the Gaussian and mean curvature respectively. So I'm just going to pause from verbatim reading for a sec, and this is why I went on that however long it edits down to 15 minutes of ranting that I did in the beginning, where now we have the first, the second, and the third fundamental forms now all related together through the Gaussian and mean curvature. And this is the first page of reading section 59, and in order to get there we had to appreciate, the formulae of Weingarten as well, but we finally got here. We have K times Roman numeral 1 minus 2H times Roman numeral 2 plus Roman numeral 3 equals 0. It's one of those 1-inch long summary equations that physicists and mathematicians love because it boils all that stuff into one nice, elegant little formula. Anyways, continuing on reading. So in order to prove this relation, it suffices to give the proof with respect to a special coordinate system on a surface capital S under consideration, because capital K, capital H, and the three fundamental forms are independent of the coordinates. More precisely, mean curvature may change its sign under a coordinate transformation, but in this case also, the second fundamental form changes its sign, and the product of The mean curvature with the second fundamental form is therefore invariant. We choose coordinates on the surface capital S, so the coordinate curves are lines of curvature on that surface capital S. Then we have components of the first and second fundamental forms, namely G sub 1, 2 equals B sub 1, 2, which equals 0, for which refer back to 41.6. And Gaussian and mean curvature are given by the relations in 41.11, namely capital K is equal to B sub 1, 1 over G sub 1, 1, then times B sub 2, 2 over G sub 2, 2. And then we have capital H is equal to 1/2 times the quantity B sub 1, 1 over G sub 1, 1 plus B sub 2, 2 over G sub 2, 2 closed quantity. So by means of the formulae of O. Rodriguez, and I'm just going to read those off really quickly here. We have M sub alpha equal to negative B sub alpha alpha over G sub alpha alpha, then times the vector X sub alpha, where alpha is equal to 1 or 2. Namely, key here, do not sum with respect to alpha. Okay, this is not to be confused with the Einstein tensor summation notation that is laid in throughout the previous 15 sections. So we have n sub alpha being that, or we also have vector x sub alpha plus capital R sub alpha times vector n sub alpha is equal to a 0 vector, where capital R sub alpha is equal to the reciprocal of kappa sub alpha, or 1 over kappa alpha, where alpha is 1 or 2. Those are the formulae of O. Rodriguez. So by means of these formulae, we thus find that C sub 1, 1 is equal to the scalar product of vector n1 with vector n1, which is equal then to the square of B sub 1, 1 over G sub 1, 1. Taking that square and then multiplying that times the scalar product of vector x sub 1 with x sub 1. This then equals B sub 1, 1 squared over G sub 1, 1. That is what C sub 1, 1 is equal to. We similarly have that C sub 1, 2 is equal to 0, and C sub 2, 2 is equal to B sub 2, 2 squared over G sub 2, 2. I say G sub 2, 2, B sub 1, 2, etc. I'm not saying B sub 22 or B sub 12, because there are two indices of these components of the fundamental forms. And there's a first and a second one. So by means of the definitions for Gaussian and mean curvature, the relation Gaussian curvature times the first fundamental form minus 2 times mean curvature times the second fundamental form plus the third fundamental form equals 0. That follows from those expressions. So comparing in that united term for the fundamental forms, the terms which contain du1 squared, du1 times du2, and du2 squared respectively, we immediately obtain the relations C sub alpha beta equals 2 times capital H times B sub alpha beta minus capital K times G sub alpha beta, where alpha and beta are respectively 1 or 2. From the relation C equals B squared over G, we find the following geometrical interpretation of the Gaussian curvature. Theorem 59.1, due to O. Rodriguez. At any point of a surface capital S, the absolute value of the Gaussian curvature capital K of the surface capital S is equal to the quotient of the element of area d capital A star of the spherical image of capital S and of the corresponding element of area d capital A of S. The proof is as follows. I'm going to do a little whiff of the salts before getting into this proof. I did this back in the third or fourth reading stream that I did, and that was when I first opened this, right? The first whiff upon immediately peeling the plastic off of this was the strongest with by far. And I read the instructions and you're supposed to put a little bit of water on to like activate the ammonia or whatever. So I did that and it was not as strong as that first one, but I've gotten, you know, a little bit strong whiffs out of this over time, but still none compared to the first unpeeling the plastic one. So that's, I will have that to say about this in this little impromptu review of these smelling salts. But I might say that that is because when I smell my cat's litter box, when I'm cleaning his litter box, that, by the fact of me routinely cleaning my cat's litter box, might mean that I'm desensitized to like whatever formula of ammonia salts that this is. Or maybe I just like, by having a cat, in order to get the like full effect of ammonia smelling salts, I need like a way stronger kind. Because I was noticing when I would clean my cat's litter box, I'm like, I wonder if this like wakes me up or whatever, and I just don't realize it. You know what I mean? But so let's just do a little bit. Right, like I'm just like, there's still a little bit of water in here, so it's like if I don't know. The proof is as follows. By means of 36.8, which is that the element of area of a portion, capital H, not to be confused with the mean curvature, capital H, but a portion, capital H, of a surface, capital S, that element of area is given by d capital A, which is equal to the square root of g, referring to the discriminant of the first fundamental form, then times du1, then times du2. So by means of that, as well as 41.9, which is just the definition of Gaussian curvature, capital K is equal to the product of principal curvatures, kappa 1, kappa 2, which is equal to the discriminant of the second fundamental form B over the discriminant of the first fundamental form G. By means of that, we have d capital A star over d capital A is equal to square root of C over the square root of G, which is equal to the magnitude of B over the square root of G, then times 1 over the square root of G, which is equal to the magnitude of capital K. Straightforward calculation proof. Remark, if we use the concept of an oriented element of area, we may formulate the previously given theorem 59.1 as follows. If the spherical image capital S star of a portion of a surface, capital S, is oriented so that the normal vectors to capital S, the portion, and capital S star, the spherical image, have the same sense that at any point capital P of capital S, the quotient dA star dA of the corresponding oriented elements of area equals the Gaussian curvature capital K of the portion capital S at the point capital P. Theorem 59.1 is due to O. Rodriguez and occurs later in the general theory of Gauss. Okay. This theorem states a fact which is analogous to the one given by the relation in section 17. Which, did I write that down? The spherical image of a portion of a surface is, in general, a portion of a surface. However, in the case of a plane, the unit normal vector is constant, and the spherical image therefore degenerates into a point. If capital S is a developable surface, then the unit normal vector n is the same for all points on any generating straight line. Hence, the spherical image of a developable surface degenerates into a curve. Therefore, by the previously just given theorem 59.1 of O. Rodriguez, capital K equals 0, or namely the Gaussian curvature is equal to 0, that must hold in this case. Therefore, we can prove the following. Theorem 59.2. A portion capital S of a surface of class R greater than or equal to 2 is a portion of a developable surface if and only if its Gaussian curvature capital K is 0 everywhere. The proof is as follows. Part A. The spherical image of a developable surface is a curve. See above. Hence, in consequence of the theorem of O. Rodriguez, theorem 59.1, the Gaussian curvature is equal to 0 at any point. Part B. If we assume conversely now that the Gaussian curvature is 0, then by means of the definition of Gaussian curvature being equal to the product of principal curvatures, which then calculates out to being the discriminant of the second fundamental form over the discriminant of the first fundamental form, then also b equals 0, where b is the discriminant of the second fundamental form. Now, if b sub alpha beta is equal to 0, where alpha is equal to 1 or 2 and beta is equal to 1 or 2, respectively, the surface is a plane, for which we can refer back to problem 45.1. If b equals 0, that is, b sub 1, 1 times b sub 2, 2 is equal to the square of b sub 1, 2. So just taking the definition of the discriminant of the second fundamental form, setting that equal to 0, and then moving that square of b sub 1, 2 term over to the other side, having everything be positive. But b sub alpha beta are not all 0. Then by this rearranged version of the set to 0 discriminant of the second fundamental form, the differential equation of the asymptotic curves on a surface, so b sub alpha beta times du alpha times du beta is equal to 0, that differential equation of the asymptotic curves can be written in the form where the quantity square root of b sub 1, 1, then times du1 plus square root of b sub 2, 2, then times du2, closed quantity squared, is equal to 0. That is, we have only one family of asymptotic curves, as is the case for parabolic points. The coordinates on the portion capital S of the surface under consideration may be chosen so that the curves u2 equal to a constant coincide with the asymptotic curves. Then on these curves, du2 is equal to 0. Hence, in consequence of this previously given form of the differential equation for the asymptotic curves on the surface, b sub 1, 1 equals 0. And in consequence of the rearranged version of setting the discriminant of the second fundamental form equals 0, then also b sub 1, 2 is equal to 0. By means of the formulae of Weingarten, which you can look up what the exact formulae are, we obtain from this that the vector n sub 1 is equal to negative b sub 1 superscript beta, then times the vector x sub beta, which is equal to the negative quantity b sub 1, 1 times g superscript 1 beta plus b sub 1, 2 times g superscript 2 beta, closed quantity, times the vector x sub beta, which is equal to a 0 vector. That is, the unit normal vector n is independent of u1, and consequently, the vector n does not vary along any asymptotic curve. If the asymptotic curves are straight lines, then capital S is a portion of a developable surface which has those lines as generators. This indeed is true. Since b sub 1, 1 equals b sub 1, 2 equals 0, and b sub 2, 2 is non-zero, we obtain from the first of the equations, which are consequences of the formulae of Menardi-Codazzi, that Christoffel sub 1, 1 superscript 2 is equal to 0. Therefore, the formulae of Gauss takes the form vector x sub 1, 1 equals Christoffel sub 1, 1 superscript 1 times the vector x sub 1. That is, the asymptotic curves are straight lines, for which we can refer back to problem 11.1. If all b sub alpha beta, or if all components of the second fundamental form, that is, are 0 along a straight line, then capital S has flat points on that line. For developable surfaces, this may happen and does not contradict theorem 58.3. Namely, that every developable surface with a vector parametric representation of x in terms of s and t can be subdivided into sufficiently small suitable s intervals, arc length intervals that is, so that the portion of the surface corresponding to any of these intervals is a portion of either a plane, a cylinder, a cone, or a tangent surface. Developable surfaces are important because of the following property. Theorem 59.3. A sufficiently small portion of the surface of class r greater than or equal to 3 can be mapped isometrically into a plane if and only if it is a portion of a developable surface. The proof is as follows. Part A. The Gaussian curvature K is invariant with respect to isometric mappings, for which refer back to Theorem 57.2, which states that isometric surfaces have the same Gaussian curvature at corresponding points. Corresponding curves on these surfaces have the same geodesic curvature at corresponding points. In the case of a plane, we have that Gaussian curvature K is equal to 0. Hence, in order that a portion S of a surface can be mapped isometrically into a plane, we must necessarily have that Gaussian curvature K is equal to 0. That is, in consequence of Theorem 59.2, as previously given, S must be a portion of a developable surface. Part B. We will now prove that a sufficiently small portion S of a developable surface can be mapped isometrically into a plane. We introduce on S geodesic parallel coordinates u1 and u2 so that the curve u1 equal to 0 is a geodesic G. The curves u2 equal to a constant are geodesics which intersect G at right angles, and the curves u1 equal to a constant are geodesic parallels of G. As was pointed out in section 52, by means of a suitable choice of u1, the first fundamental form is then given by the expression as per ds squared equal to du1 squared plus g sub 2 in terms of u1 and u2 then times du2 squared. Moreover, if we take the arc length of G as coordinate u2, then ds is equal to du2 on G, and therefore g sub 2 in terms of 0 and u2 is equal to 1. Since G is a geodesic, from 49.9a, which is that kappa sub g, where u1 is equal to a constant, is equal to 1 over the quantity 2 times g sub 2, then times the square root of g sub 1, then times partial g sub 2 over partial u1, which then is equal to 1 over the square root of g sub 1, then times partial with respect to u1 of the logarithm of the square root of g sub 2. From this, we have that partial g sub 2 partial u1 evaluated where u1 is equal to 0 is then 0. In consequence of the previously given Theorem 59.2, Gaussian curvature K is equal to 0 on S. Hence, the equation for Gaussian curvature for geodesic coordinates takes the form partial squared of the square root of g sub 2 partial u1 squared is equal to 0. Integrating this relation, we find that the square root of g sub 2 is equal to c1 of u2 times u1 plus c2 of u2. It follows from g sub 2 at 0 and u2 being equal to 1 that c2 equals 1, and from partial g sub 2 partial u1 evaluated at u1 equal to 0 being 0 that c1 equals 0. Hence g sub 1 equals 1, g sub 1 equals 0, and g sub 2 equals 1. If u1 star and u2 star are Cartesian coordinates in the image plane, the mapping u alpha star, which is equal to u alpha, where alpha is equal to 1 or 2, is isometric in consequence of Theorem 57.1, which is that an allowable mapping of a portion S of a surface onto a portion S star of a surface is isometric if and only if, at corresponding points of capital S and capital S star, when referred to the same coordinate systems on capital S and capital S star, the coefficients of the first fundamental forms on capital S and capital S star are the same. That is, G sub alpha beta is equal to G star sub alpha beta, where alpha is equal to 1 or 2 and beta is equal to 1 or 2, respectively. We mentioned the following results of the preceding investigation. The orthogonal trajectories of geodesics on a developable surface are also geodesics on this surface if at least one of them is a geodesic. This property holds on developable surfaces only, since otherwise also surfaces other than developable ones can be isometrically mapped into a plane, in contradiction to theorems 57.2 and 59.2. It was already known to Leonard Euler and Gaspard Monge that there are developable surfaces other than cones or cylinders. And I thought I was going to get into section 60, but we're going to leave that for next time. I will see you guys in the next one. Peace.